Hello, and welcome to our video on complex powers. Here is our motivating question. How should we define the expression a to the z when a and z are complex numbers? If we're in the case where z is an integer, then there's a pretty natural definition of a to the z. You multiply a by itself z times, and if z is negative, you divide. But what happens when z is not an integer? Let's think back to what we did in the real case. At some point in calculus, we specified the following. If a is a positive number and x is a real number, then you define a to the x is equal to e to the power x times natural log of a. And of course, we're defining e to powers by the power series definition of e. So with this definition of a to the x in real-valued calculus, you get all the properties of exponentials that you would expect. Their interaction with natural logs, their derivative properties. It's a very nice and clean way of defining a to the x. And so we're motivated to use the complex log to define complex powers. If we have a number a that's non-zero and any number z in the complex plane, then we'll set a to the z to be equal to e to the z times log of a. And of course here I'm not using any particular log like the principal log. This is going to be a set-valued or multi-valued expression. So this is really the set of all numbers of the form e to the z times natural log of modulus of a plus I times principal argument of a plus 2 times pi times I times k for k an integer. So a to the z is typically multi-valued, and if we want it to be single-valued, we would have to specify a branch of the logarithm. We would have to specify an interval in which the values of the argument that appear in the definition of the log live. As an example, we'll calculate the seemingly bizarre expression minus 1 raised to the power I. So by definition, minus 1 raised to the power I is equal to e to the power I times log of minus 1. Now, e to anything is going to be given by the power series definition of e, so we know what that expression should be. But what about this I times log of minus 1? Here we are most certainly using the complex log because I'm trying to plug a negative number into a log, and so this is going to give me the multi-valued expression. We calculate log of minus 1 is natural log of the modulus of minus 1 plus I times the argument of minus 1. And here I'm using lowercase argument, so this is going to be a set-valued expression. So this is natural log of 1 plus I times the principal argument of minus 1 plus 2 times pi times I times k, where k can be any integer. So what is the argument of minus 1? Minus 1 is a number over on the negative real axis. You have to rotate a distance pi from the positive real axis to get there. So log of minus 1 is natural log of 1 plus pi times I plus 2 times pi times I times k for k an integer. And natural log of 1, of course, is 0. So this collapses to pi times I plus 2 times pi times I times k. And this factors nicely as 2k plus 1 times pi I. So minus 1 to the I, this symbol, is all numbers of the form e to the I times 2k plus 1 times pi I for k an integer. And so that becomes e to the minus 2k plus 1 times pi. So minus 1 to the I is a multi-valued or set-valued expression. It is the case that every element of this set minus 1 to the I is a positive real number, but there are infinitely many elements to that set. And as always, when we're dealing with logs, arguments, powers, if you see a k somewhere in what I'm writing, I really mean k as an arbitrary integer. So ultimately, log of minus 1 or minus 1 to the I both involve sets. Minus 1 to the I is the set of all numbers of the form e to the minus 2k plus 1 pi for k an integer. Here's a thorny question. Do we have e to the z raised to the power w equals e to the z times w? Now we're going to interpret, as always, e to the z and e to the product z times w as the power series version of e, so these are single-valued expressions. But on the left here, this number e to the z raised to the power w, if z and w are going to be complex, I have to use the complex power, so that left-hand side is going to be a set of numbers. So my question is this set of numbers equal to the singleton e to the power z times w? So by definition, e to the z raised to the w is equal to e to the w times log of e to the z. And we saw before that log of e to the z is a multi-valued expression. So this becomes e to the w times z plus 2 pi I times k, where k can be an arbitrary integer. Now I multiply in the exponent and I split apart the exponential, and I get e to the z times w times e to the 2 times pi times I times k times w, where again, k is an arbitrary integer. And of course, when we see a 2 pi I k in an exponential, our instinct is to say, oh, that's just going to be 1. But this exponential has the w. It's e to the 2 times pi times I times k times w. So e to the z raised to the power w is a whole set of numbers, depending on the integers. And if w is an integer, then yes, e to the 2 times pi times I times k times w is equal to 1. And the whole set above just collapses to a singleton, and we get e to the z raised to the power w is the singleton set containing e to the zw. But if w is not an integer, then I'm going to claim that e to the 2 pi I kw will have at least two distinct values that will depend on k. For example, what if we took w equal to 1/2, so we were looking at a square root of e to the z? Then we would have e to the 2 pi I kw is equal to e to the pi I k, and that we know is minus 1 to the k, which will alternate between values plus 1 and minus 1. And so in this case, e to the z raised to the power 1/2 would be the multi-valued expression plus or minus e to the z over 2, where we know that e to the z over 2 is given by the power series for the complex exponential. Or you could take w equal to I, and in this case you would have e to the 2 pi I kw equals e to the minus 2 pi k, and so e to the z raised to the power I is really the set of numbers e to the iz minus 2 pi k for k an integer, and this has infinitely many values. So familiar rules of powers, familiar rules of exponents, don't necessarily carry over to the complex numbers. Even this sort of associativity of powers, e to the z raised to the power w, doesn't have to reduce to e to the z times w. So this is an ambiguity of which you should always be careful when you're working with complex powers. The happy news is that most of the time when we deal with a complex number raised to a power, it's going to be an integer power, positive or negative. So in practice, this ambiguity doesn't occur all that often, but watch out for it.